Okay, this problem is pretty straightforward. You just need to pick the stronger acid, and that is just a matter of recognizing that the larger the Ka, the stronger the acid. So HOCl has a Ka of 2.9 times 10 to the minus 8th. So I'll just show you this part of it. And the second part of the question, which I actually didn't show, is to draw the Lewis structure for that acid. So just remember to follow the octet rule, and also remember the rule that oxygen forms 2 bonds and hydrogen 1. Okay, this question I just went ahead and showed the answer, and I just want to talk about it a little bit. So the question is, which of the two acids is stronger? Really the best way to explain that is the second option here. This is the way it's done more frequently in chemistry. The way that you explain whether an acid is stronger or weaker has to do with the stability of the conjugate base. So OCl minus is more stable than OI minus, and this is because Cl is more electronegative, and that makes it better able to accommodate or deal with the negative charge. So conversely, that means that the OI minus is less stable, means that the acid is weaker. Okay, for the first question, you just want to write the reaction, so that's pretty straightforward. For the second one, even if you aren't given the equation, you should recognize that NaOCl is going to act like a base in water. The sodium is a spectator ion, and the OCl minus ion is the conjugate base of the weak acid HOCl. So then if you want to write that, it just looks like so. And then finally, you need to calculate the value of the equilibrium constant. So, what can you do here? You have the Ka, and you're looking for the Kb, and you will use the relationship that we've talked about many times in the past, that Ka times Kb is equal to 1 times 10 to the negative 14th. So that enables you to get the value of Kb. At this point, you have all of the information that you need in order to solve for the OH minus concentration. You have Kb, you have the equilibrium expression, you're given the concentration, so this one is pretty straightforward at this point. So it's just a matter of substituting into the equation, making the ice table, and when you do that, so down here, you end up with the OH concentration. And you could just as easily have been asked to get the pH, which you could do without much trouble. In the first part of the problem, you know the pH, and you're wanting to find the H3O plus concentration, so you know that you do 10 to the minus pH in order to get that. The second part of the problem wants to know whether you have more HOCl or OCl minus in the buffer. In a way, this is a matter of comparing the pH to the pKa, or you could compare the H3O plus concentration to the Ka, and I think that's the way that it's done here. So, if you look down at this part of the problem down here, so you're solving for the OCl minus here. You're solving for the ratio of OCl minus to HOCl. And you see that when you do that, it's much less than 1, and that means that the HOCl is greater, the concentration of the HOCl is greater. In this question, it's kind of a lab-based question, so you're given information about an experiment that's set up, and you know the volume of a flask, you know the mass of the flask with air, and you know finally the mass of the flask with when it's been filled with an unknown gas. So the first part is you want to determine how much the mass of the dry air is, and you're given the density. So that's a pretty straightforward calculation. So you just solve the density equation for mass, so that gives you the mass of the air. Then define the mass of the flask without anything in it, what it would be if you had nothing in it. You just do what? You subtract the mass of the air from the mass of the flask plus air. Then finally, if you want to find out how much the gas weighed that was put into it, so you just subtract the mass of the flask from the mass of the flask with the unknown gas, and that will give you the information that you need there. So that gives you the number of grams that you have in the flask. For the next part of the problem, you want to find the molar mass of the gas. Well, you know the grams of the unknown gas, you just found that. So what else do you need to know? So you need to find the number of moles of the gas. So you could use PV equals nRT and find the moles, and then divide the grams by the moles, and that would give you the molar mass. So that's the approach that's taken here. Of course, it probably goes without saying, but I will say it anyway, remember to get everything into the right units. Primarily, this means getting the pressure into atmospheres. You could use a little bit different approach, but I think the first one is more straightforward in this case. And the last part of this question is, well, maybe not the very last, but the next part of this question is to find the percent error. So remember, it's the absolute value of the difference between the theoretical and the experimental divided by the theoretical. So the student's answer was lower than the actual or the theoretical answer. So these are two situations, and you're asked to evaluate if they would explain why the student's answer was lower. So in the first case, you're told that not all of the air was removed, and since air has a lower density than, or lower density and mass than the CO2, then that would in fact make the answer lower than it should be. So I think that that's right. Second one's a little trickier to deal with. So what it's saying there is we assume that the temperature of the CO2 was 23, but it was actually lower. So if you go back to when we solved for use PV equals nRT, and you just realize that we had a higher temperature than we actually had, so that made the number of moles smaller, which made the molar mass higher than it should be. In other words, this mistake would have done that. So this is not considered to be a good explanation, or this occurrence wouldn't have accounted for that particular error. For this part of the problem, the question is asking to come up with a way to find the volume of the flask. I think we probably did this a couple of times. So one of the things you can do if you want to find the volume of something is you can fill it with water, and then you can weigh or determine the mass of the amount of water and assume that the density of water is 1 gram per cubic centimeter. The first part of this question is just a limiting reactant question, so you could do this one of two ways. You could go through with both of the amounts that you are given, so that would be the 25 grams of methane and the 2.58 moles of the CO2, and figure out which one would give you the smaller amount of what's being asked for a little bit later in the question. Or you could just reason it out. You could change the 25 grams of methane into moles, and since you know that there's a 2-to-1 ratio up here, if you don't have that, then you can figure out which one is the limiting reactant that way. So I think the choice here was to do it the second way that I described. So let me see if I can remove this. There we go. Yeah, so what they did in this problem is figured out basically how much Cl2 you would need to react with the 25 grams of CH4. So same sort of idea. And then finally, for the next part, you just find how much of the CH2Cl that you can make with the limiting reactant. So this is the theoretical yield, just in moles, not in grams. In part B, you are asked to calculate the energy in joules necessary to break a single Cl-Cl bond, and this is really just a matter of making the conversions. So you are told at the beginning that it is 242 kilojoules per mole, so you need to change kilojoules to joules, and you need to change moles to the amount for a single bond, and that is done here. So that gives you 4.02 times 10 to the minus 19th joules. For part C, you need to calculate the wavelength of light that would supply enough energy to break that bond. So you can go from joules to frequency, and then frequency to wavelength, and that should do it. So we did that earlier. It's reasonably straightforward. So those are the two parts of the problem here, and obviously you're given the two equations over on this side. So you're given this one, it may be in a slightly different form, but you're given those two equations. Part D, you're shown a mechanism with several steps, and you are asked to determine if CH3Cl is a catalyst or an intermediate. So remember, a catalyst is something that is added to initiate the reaction or to lower the activation energy, and it is regenerated at the end. An intermediate is something that forms and then in one step, and then it gets used up in another step. So let me see if I can do this. So here we have CH3Cl, which is produced there, and then it gets used up in this step. So that means that it's an intermediate. Also, in the next part of the problem, we're going to have to come up with the information for the rate law. So let's observe that here, just do it like this. This is the slow step. So for the slow step, we could write rate equals CH or K times CH4 times concentration of Cl. Now notice that Cl is not in the overall equation, and so we'd have to make a substitution here. Let me use a different color. So we would have to substitute an expression using the fast equilibrium in order to have reactants that are actually part of the reaction as written. So that's what we have here. So the slow step was the one involving CH4, and here's what I was talking about just a second ago. So there we have the rate. The problem is we have to make this substitution for Cl. This one's a little different than what we normally have because you do have an exponent of 1/2, and the way that comes about is here, do this a little bit differently. Okay, the way that comes about is when you have this part of the equation and you solve it for Cl, that gives you Cl2 to the 1/2, and then that's the substitution that you have to make here. So you're substituting the expression in step 1, the one that I marked up there, and then that gives you the overall rate equation. The principle is the same as what we've done before. You find the rate, or you find the slow step, and that gives you the rate. If that rate contains something that is not in the equation, meaning the overall equation, then you have to make a substitution. So typically you take the equilibrium step, rearrange that and, so that it's solved for what you have in the slow step, and then you make the substitution. It's actually harder to say in words than it is to do, but you can take a look at this and see if that makes sense to you. I think you might find this one hard. Students normally find these kinds of questions difficult, but the idea here is that the carbon is going to take the place of the iron. And when that happens, you end up with, I think this is probably the more straightforward equation. So the carbon takes the place of the iron, and you get CO2 and iron. So it's kind of a single replacement reaction. For the second part, just to get the oxidation numbers, I think that that's not too difficult, because if you look on the left side, the carbon's not combined with anything, so it's 0. And on the right side, it's combined with oxygen. So the oxygen takes precedence, it's -2, and there's 2 of them, so it's -4, so the carbon would be 4, +4. Okay, for this problem, you have ammonia, which is a weak base, and you have hydrochloric acid, which is a strong acid. You're going to mix equal molar volume, so essentially equal moles of those two, and you want to write the equation. So you have ammonia, which is an H3, and then for the hydrochloric acid, you just show only the H plus for that. So you could write it either of these two ways. The second part of the problem wants to know if the solution that you form is acidic, basic, or neutral. Well, if you think about it, so here we have a, what is that? An H4 plus is a weak acid, so the solution is going to be acidic. So, new problem. This is a thermo-based problem, so you're given a fair amount of thermodynamic information for 3 different reactions. In the first part, it says to write the Kp for the first reaction, and just remember there to only include the gases. So I think that one is okay. For this part of the problem, you want to know again, for the first reaction, is the value of the equilibrium constant going to increase, decrease, or remain the same if the temperature is increased. If you look back on the previous page where the data was, then you'll see that the delta H is positive, so that means the reaction is endothermic. That means that heat is a reactant, so that means if you increase the temperature, the reaction should move toward the right, and that should make Kp a larger value. You can also reason this out using the Gibbs equation, but I think it's probably more straightforward just to use Le Chatelier's principle for this one. So let's just talk about the answer to this one. So you'd have to look back to the previous data, but you're told that for reaction Y that delta G is positive. So remember, that means that the reaction is not spontaneous, and that is equivalent to saying that you have an equilibrium constant less than 1. That's probably the most straightforward way to do it. You can also do it using the equation that's given here. You can use this one and reason it out the same way, but again, I think the second choice here is the more straightforward way to answer this one. So if you look back at the table, we see that for this reaction Y, that the reaction is endothermic. This means it takes more energy to break the bonds of the reactants than is released when the products form. So that means the bond energy of the reactants is higher. So I'll show you that. So that looks like that. And then the next part says that you can predict that reaction Y will occur more rapidly than reaction X. And remember, thermodynamics doesn't tell us anything about the rates of the reaction. So that would be a kinetics type question, which we don't have information about. Okay, if I had this to do over again, I would put each of these individual questions under the graph information, because you need to look at that but let me just go ahead and show you the answer, and we'll just see if that makes sense. So it says that delta S for the reaction is negative because you have 2 moles of gas going to a mole of solid and a mole of gas. So yeah, that makes sense. Then for the last question, the third reaction, what they're calling reaction Z, is a combination of the first two. So yeah, so that's all you have to do is just add the delta H's for those. Okay, so you have the reactions in front of you, and you should see that if you start and you have a situation where you only have reactants, then the reaction will go to the right. And what happens is that you get a conversion of 2 moles of gas, 2 moles of CO, to 1 mole of CO2. So you are basically reducing the moles of gas. So that means that the pressure should decrease. So hopefully that makes sense to you. And for the last two, these are pretty straightforward, just electron configuration questions, so I don't really have a lot to say about that. Okay, so you would have for sulfur 1s2, 2s2, 2p6, 3s2, 3p4, and then the anion you gain 2 electrons. Part 2 wants to know why the radius of the S2 minus ion is larger than the radius of the sulfur atom. So here's what you can't say for an answer. You can't say that when atoms gain electrons, they become larger. That's really considered just a restatement of the fact that was already given. So you need to put your answer in terms of greater repulsion, same nuclear charge, but greater repulsion between the electrons. Okay. Then for the last part of this, the question has to do with something being attracted in a magnetic field. So that depends on whether or not you have unpaired electrons in orbitals. So the S2 minus, once sulfur gains 2, it has all of its electrons paired. And so the sulfur would have had 2 unpaired electrons. So that's the one that would have been attracted. So that the word for that is paramagnetic. So be sure that you know or remember what the word isoelectronic means. It means that you have the same electron configuration. So the S2 minus ion, sulfide ion, is isoelectronic with argon. The difference between the two is that argon has a greater nuclear charge. And that means that it's going to be harder to remove those electrons. Well, actually the question asks which one is easier, so okay, fine. S2 minus is easier to remove electrons than the argon. Last one is a little bit of a tricky question because it asks about the bond angles. This one I think would be a little bit hard for you. So normally we would predict for this one hybridization so that the angle might be more like 109, but they tell us that the angle is close to 90, and what you have to realize, if it's close to 90, 90 corresponds to p orbitals. If you remember that the p orbitals are all 90 degrees from each other, so this one would look like this. So you are asking this problem to compare the intermolecular forces in H2S and H2O, and the thing to know there is that H2S has a higher molar mass and more electrons, so that's going to make the London dispersion forces stronger. With a comparison of H2S and H2O in terms of dipoles, that's a matter of difference in electronegativity. And so in this case, the water is going to be, or have a stronger dipole, basically, than H2S. Of course, water also has hydrogen bonds, so I don't know, they didn't mention that in the answer, but it would be fine if you said that as well.